My name's Kareem Khalifa. Today, we'll be covering formal methods for conjunction and disjunction. Today, we're just going to look at the introduction and elimination rules for conjunction and disjunction, that is, and or. Let's begin with conjunction elimination. This says, from a conjunction, infer one of its conjuncts. So on the left-hand side, you see we have the abstract version of this. From P and Q, infer P. And on the right-hand side, we have an example that we used from the previous lecture. Megan Rapinoe plays soccer and is from California. Therefore, Megan Rapinoe plays soccer. Let's look at a very simple application of and elimination on the right over here. We're given P and Q, and just as the rule says, we want to infer P from that. Then in the right-hand column, what we're going to do is we're going to put and elim, the rule, and the line to which we applied that rule, which is line 1. In other logical systems, you wouldn't have as much flexibility as you have with Fitch. I'm going to highlight some of the flexibility that it has. For instance, one thing you can do here is you can infer either P or Q from line 1. So you see here we inferred Q, and it would have exactly the same rationale on the right-hand side. Similarly, when you have conjunctions with 3 or more conjuncts, you can infer any one of the conjuncts that you want, as we did here. So we inferred R from P and Q and R using and elimination. And note that we haven't changed anything in that right-hand column in line 2. And here's yet another way in which Fitch is incredibly flexible compared to some other logical systems. Suppose we have 3 or more conjuncts in a conjunction, as we do on line 1 of this proof. We can grab any 2 of them and pull them down as their own conjunction, as we've done here. So we could put R and P, as we did on this line. We could do P and Q, we could do P and R, we could do Q and P, etc. Fitch is even really flexible about parentheses so long as everything you're dealing with is a conjunction. So for example, this is really no different than what was on the previous slide. We've just added parentheses, and we can run exactly the same rule. Fitch is cool with that. However, things are different when you start putting in other logical connectives. For now, we'll just focus on or, because that's really the only one that we can use. In this case, it would not be okay to infer R using and elimination in line 1, unlike the previous case where that or was an and. However, because the whole complex expression Q or R is one of the conjuncts in line 1, you can infer that as a chunk, as it were, and that would just be another application of and elimination. The next rule that we will look at is called conjunction introduction. This says if you're given P by itself and Q by itself, you can infer the conjunction P and Q. For example, if we are told that Iron Man is an Avenger, and we're also told that the Hulk is an Avenger, then we can infer that both Iron Man and the Hulk are Avengers. Stated more abstractly, suppose that we're given P as a line in our proof, and we're given Q as a line in our proof, then we would write P and Q, then put next to it and introduction, and the lines that motivated that conjunction, the lines that we applied and intro to, which in this case would be 1 and 2. So note that you're always going to need at least 2 lines or 2 numbers that you put next to an and intro in a proof. As with conjunction elimination, Fitch is pretty generous when compared to other logical systems. For instance, in the proof that you see here, you don't have to do 2 applications of and intro. You just have to do 1 and list 3 lines next to it, 1, 2, and 3, because that's what's justifying the application of and intro in line 4. Also, parallel points about parentheses in conjunction elimination also apply to conjunction introduction, so keep that in mind as well. For the third rule that we'll discuss today, we'll talk about disjunction introduction, or intro. This says, from P, infer P or Q. For example, Frida is a dog. It follows from this that Frida is a dog or a dragon. Frida, you're not fooling anybody. Here would be a basic application of or introduction in a proof. So you're given P, and then you can write down P or Q, and what you put as your rationale in the right-hand column over there is or intro and line 1, which serves as the trigger, as it were, for the or introduction. As with the previous rules that we discussed, Fitch gives you a few shortcuts that you don't see in other logical systems. For instance, you could have an arbitrarily long disjunction, P or Q or R or S, etc., 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 and it would work in just the same way. Parallel points apply about a parentheses, as we talked about before, but now we're talking about disjunctions rather than conjunctions. So far the proof techniques that we've used are relatively straightforward. This one requires a little bit more thinking. This is called disjunction elimination, what we called proof by cases in the previous lecture. Here it is stated abstractly. Suppose you have an arbitrarily long disjunction, P1 is the case, or P2 is the case, or etc., all the way to Pn. And from each of those disjuncts, you can infer the same statement S. Then you basically know all roads lead to S, is the way that we put it last time. So you can infer S, right? So here's the example we used from the previous slide. You're damned if you do and you're damned if you don't. So either you do something or you don't, right? If you do it, you're damned. If you don't do it, you're damned. Therefore, you're damned. That would be an example of this. All roads lead to damnation, if I can put it that way. Now, it turns out that we can't even prove something like you're damned if you do and you're damned if you don't at this point because we don't actually have if-then, which is crucial for that kind of reasoning. However, we can prove other kinds of disjunction elimination, so let's look at those. For example, if we know that either P and S is true or Q and S is true, then we know that S has to be true. Let's make sure we understand the mapping of this inference onto the rule. In this case, we have a disjunction, and each disjunct is a complex expression. So P1 is going to correspond to the conjunction P and S. And the only other disjunct, Pn, as it were, is going to correspond to the conjunct Q and S. S is going to be a consequence of each of these things, right? From P and S, you can infer S using and elimination, and from Q and S, you can infer S using and elimination. So all roads lead to S, and we can apply disjunction elimination. Let's see what this looks like in a Fitch-style proof. So here's a very, 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 very preliminary sketch. We know that our premise is going to be either both P and S or both Q and S. Furthermore, we know that our conclusion is going to be S. We also know that we're going to get there by way of OR elimination, and obviously that's got to involve the disjunction in the first step of the proof, but we don't know really anything else that's going on. And so what we want to do is talk about that. Here's one way of thinking about it. What's preventing us from applying the rule at the bottom of this slide, right? It's basically that we haven't yet established the fact that S can be proven from each of the disjuncts in step 1. That's what we need to fill out. And here's a funny thing about that. If we look at this, this is almost like a meta proof, right? So the whole thing itself is a method of proof, right? What we call proof by cases, right? But on top of that, right, we see that S needs to be proven from each of the disjuncts. So we need what's called a subproof within this proof, a proof within a proof, as it were. And that's what we're going to look at now. So the rule for OR elimination says that for each disjunct, we need to prove that S follows from it. Right? So the first disjunct we have is P and S, and so we need to prove that S follows from that. That'll be the first subproof we need to do, and then we need to do it for the next disjunct, and obviously if this were a more complex OR statement, we would need to do it for the third disjunct and the fourth disjunct and so on and so forth. But let's just start with the first one. Right? Our first disjunct is P and S, as you can see on line 1. And from that, we need to then have a subproof from which S follows. Let's look at line 2. P and S isn't something that's actually true. It's something like a hypothesis. I like to call these subproofs worlds of hypothesis. Right? They're sort of hypothetical worlds. You can't assume what's happening in the world of hypothesis is actually happening in the actual world, which would be the one that's represented by that leftmost proof. Right? All we know that happens in the actual world is what's on line 1. Right? Either P and S is true or Q and S is true. So we clearly can't infer from that P and S is in fact true. It's just one of two possibilities. And what we want to show is if that possibility were to be the case, then S would follow. Now we see that in order to properly apply OR elimination, we're going to need to do this also for that second disjunct, Q and S, and that's going to constitute a second subproof. And so that's what we'll put on lines 4 and 5. Right, now, you may have noticed we haven't put anything in the rightmost column as we do in our other proofs. This requires a little bit of massaging, but I wanted to give you the big picture first before sweating those details. Let's turn to those details now. Let's begin with that first subproof, spanning lines 2 and 3. Now, just because it's a proof within a proof, you don't actually have to put anything next to P and S, right? It's essentially functioning like a premise within the subproof. And so the question then is, how do you infer S from P and S? And we know that that's just a simple application of AND elimination. So let's mark that down. Now let's look at the subproof spanning lines 4 and 5. We see that this is basically going to run exactly the same way, except we have to infer S from Q and S, that is from line 4, rather than from P and S, that is line 2. Let's explain why that is. 2 and 3 are essentially separate subproofs, so you might as well treat them as separate proofs, just like you couldn't take the premise from one argument and just use it in another argument unless the arguments were somehow connected. Same thing here. The subproofs have to be connected in a certain way, and that just has not been established within the context of the proof. We have to treat each world of hypothesis as its own world, and we can't have people traveling in and out of worlds, if you want to think about it that way. We've got all the necessary pieces now to implement a disjunction elimination. We just have to tie it all together in line 6. We just have to fill in those last few question marks. All right, so what we see when we bring the rule back in is that line 1 corresponds to the disjunction, right? The P1 or ... Pn. And then what we see is S can be proven from each of the Pi, each of the P's. In this case, 2 to 3 is one proof of S, and 4 to 5 is another proof of S. And that's exactly then what we need to put in line 6 under those question marks to complete the rule. So let's do that. So now what you see is we put OR-elim 1, 2 to 3 for that first subproof. Then we put 4 to 5 for the second subproof. Obviously, if we had more disjuncts, we'd have to put more subproofs and the numbers that correspond to them.
Thanks, and I'll see you at the next lesson.